at Siemens for some 10 years responsible for the gas turbine business, so at least the business of it I should understand. I will try to share with you some of the aspects. One argument at the beginning is, why are gas turbines important? And it turns out they have quite a few advantages. They are fast to build, not so expensive, very flexible. If you want to license them, also in countries like the States or Germany, due to their friendly environmental impact, they are easy to license. So they have many advantages, except one. You need an expensive fuel, natural gas or light oil. Heavy oil is not that easy. And so it becomes the question of how much does the gas cost versus the investment for the plant. And as a third item in Germany these days, how many days a year will you be able to run? As long as you run more than 3,000 or 4,000 hours at a decent gas price, yes, gas turbine plants, combined cycle plants are attractive. Now, how do they work? And the basics are simple. You have three components. One is a compressor, one is a combustion chamber, and the third one is the expansion turbine. And if you look what happens in those three components, in the compressor, as efficient as nearly isotropic as one can, you bring the pressure from ambient to 15, 17, 20 bars. Then in a combustion chamber, you add heat by burning fuel to bring the temperature to something like 1500 degrees. And then you expand that hot compressed air via an expansion turbine to ambient temperature again. And on the right-hand side, you see the ideal thermodynamic behavior: isobaric, isentropic compression, isobaric combustion, and also nearly isentropic expansion. So this should be simple, except for one item. The temperature T3 can be up to 1300, 1400, 1500 degrees. And then what do you do with a turbine blade rotating at 3000 RPMs in such a hot environment? Normally, steel or even nickel alloys will just melt away. So how to address that high temperature, that's one of the key items, and I will talk about that in a minute. Now, if you talk to different people about gas turbines, they will say our gas turbine can go up to 1500, others tell you 1300. And it's very important to remember what kind of a definition is used. After the flame, the temperatures might be, in this example, 1550. But in order to cool the combustion chamber, you add already some air, diluting that hot gas. So when it enters the first stationary plate, it's already cooled down a little bit. And then at the point when it enters the first rotating plate, it's cooled further down because the first stationary plate also has injected some air. And for example, GE always quotes the firing temperature, that is the temperature before the first rotating plate, while in international journals you mostly read a ISO temperature, which is kind of an average temperature. If you take all the air, all the heat input, and mix it, then you get that ISO temperature. And why is that important? With this ISO temperature, again a graph out of Professor Buron's book, you can show the efficiency via the specific power of a gas turbine alone, called the open cycle process. And you see the efficiency goes up, the blue lines with the compression ratio, and therefore a jet engine has a very high compression ratio, because there you want to get the highest efficiency out of the fuel. And the temperature is only important that you get more power, more thrust per kilogram of fluid you push through. So from this you would say, let's make the jet engine with as high a compression ratio as we can. Now with a stationary gas turbine, you often make use of the energy which is in the exhaust, and I will show an example. And all of a sudden, that graph changes. Now the efficiency is nearly just a question of that iso temperature, that meaning raising the combustion temperature makes sense, and the pressure ratio is just something that you hit the optimum operation point. And this graph hinges around that iso temperature and not on the firing and not on the flame temperature. As I mentioned, I once worked for Siemens, and in the large utility gas turbines, we have a range of power output which goes from something like 100 megawatts to 375. And after the SGTs, Siemens gas turbine, you see a number 5 or 6 that tells you whether it's for 50 cycle, so to speak European, or the 6 means for 60 cycle, usually US or Japan operation. And we have that range of powers because all the utilities, customers have different needs, therefore you have to have a range of such units. But if you want to stay in business, you have to keep developing your fleet. And what are the main knobs where you can develop? Let's just take a cross-section of the gas turbine. You bring in the air gradually and then compress it. And those large gas turbines, they have air throughput of 500, 800 kilograms a second, meaning this room is sucked empty within half a second. So it's huge amounts of it. Then the compressor should operate stably, and you should have no blade vibration because those vibrating blades break off rather quickly. And what are the development areas? Aerodynamics, to have smaller losses, and aerodynamics to avoid those vibrations. So this is mostly a field for computer guys and people measuring in turbines. Next step is you have to burn the fuel. And nowadays, the big challenge is you are asked to produce very low NOx numbers. And this requires some kind of a lean premixed combustion, and this causes then again a stability problem I will talk about in a minute. Some people even say, can we do catalytic combustion? But so far it's only research idea, and nobody is using it in a commercial unit. Then the expansion side. Again, the problem is, how do you build blades which can withstand gas temperatures of 1400, even 1500 degrees C, and make them last 50,000 hours, 100,000 hours. Why? They have become so expensive that you would not dare to throw them away when you know that one blade might cost the equivalent of a small car or even a small Mercedes. Again, what are the development areas? Aerodynamics, to make a plant efficient. Cooling technology, in order to withstand those high ambient temperatures. You have to cool those plates, choose a proper base alloy, and a good coating technique. So all those areas are important and have kept important. And to give you a feel, where are the knobs to develop? When Siemens built their first gas turbines, more or less the same frame as we have for the smaller units today, 1970, that unit had 50 megawatts output, and that ISO temperature was 800 degrees C. And that's a temperature where you still can work with some base alloy. You need no cooling, you need no coating. 85, we raised the temperature by about 220, 250 degrees. And you see the increase in power came from a better compressor, more air pushed through, better efficiency of compressor and turbine, and the remaining, the red part, was due to the increase in inlet temperature. And in 2005, you saw we increased the temperature another 200 degrees. Again, the contribution from increased mass flow, better efficiency of the component, and higher temperature. I mentioned combustion is not that trivial a problem. In old days, you took just the normal gas and fired it like you have a burner at your stove. And every particle of the natural gas collects enough air and oxygen to burn. That means for a moment you have an air-fuel ratio of 1, giving a very high adiabatic temperature. That's that reddish area. And then more air is mixing in, it cools it off till you get to the temperature with which the gas enters the gas turbine. And the formation of NOx is proportional to the temperature and the time the molecule stays at that higher temperature. So therefore you want to avoid those high temperatures, and if there have to be some, then let's stay the molecule in there as short as possible. And you do this by mixing the fuel and the air beforehand, before it burns, so you get a much leaner mixture, and if this then ignites, then the total temperature is immediately only at that level you want to achieve, and that reddish area disappears, except for a kind of a pilot flame you need to keep the flame going. And while this theoretically is simple, to achieve a stable combustion has been a very difficult thing, but in the meantime, I guess people can say we know how to do it. That is again a graph out of Professor Burov's book. I saw it the same again. So you have to bring the air in here, the fuel like in a shower head, and then you only ignite it out here and try that this is a stable combustion. As I said, it can be done, it's not trivial. Now, one of those burners might provide thermally 20, 30, 40 megawatts. Now, if the total thermal input is 500, 600 megawatts, you need more than one burner. And therefore, you assemble around the circumference some 16, 20, 24 burners. And there you see again a difference. Originally, Siemens had an open annular space and fired the 24 burners into that open annular space. It's a cheap solution, but it is very difficult to keep the combustion stable. The colleagues from GE and Westinghouse, they have for each burner a kind of a can, they call it. So each burner fires into its own separate container, and then this opens up to the first row of blades. It's more expensive, but you can test a new burner individually, one burner, and you do not have to test the whole assembly. So in the end, we also said, even though it's more expensive, let's move to that system. I mentioned another problem at the turbine side, that is withstanding the very high temperatures. We built those plants more or less like steam turbine plants out of one solid piece of metal till the 70s, early 80s. But with that design, we were only able to achieve temperatures 900, maybe 1,000 degrees. Nowadays, those blades are hollow and have some cooling air going through and taking some of the heat off. So the metal has some intermediate temperature between the outside gas and the inside cooling, and you just have to arrange it that the metal should not take more than, let's say, 1,000 degrees centigrade. By this development, the power output per blade is tripled, but the price of such a blade has gone up, let me say, by a factor of 20 or 30. Such a blade easily costs as much as a small car. Again, a photo out of Professor Buro's book. It's a rotating and a stationary blade. And the interesting thing are those rows of holes. What are they for? Originally, we had a cooling only by getting cooler air at the inside of the gas turbine, taking the heat off. But with the intent raising the gas turbine temperature further, we went to a cooling technology where part of that cool air comes out here, for example, at the nose or close to the nose, comes out and puts itself like a thin layer of cooler 400-degree air and protects the surface from the mainstream, which might have 1400 degrees. So the inside of such a blade is a rather complex structure, and the casting technology is the same as the old Egyptians used for casting, for example, their jewelry. What kind of material is used? Basically some nickel alloys. And the question is, if you cast it as an amorphous substance, then it can take a certain temperature, because at the interfaces of the crystalline grain, there usually the first deterioration starts. If you are able to cast it in a way that the boundaries of the grains are along the centrifugal force, you gain some 25 degree, which that blade can withstand. And if you cast the whole thing as one single crystal, which is quite a complex technology, you gain another 50, or altogether 50 degree, which means you improve the efficiency maybe by 1 or 2 percentage points by doing that. The blade might be more costly, but 1 percentage point of a higher efficiency means you can sell that plant for maybe 10% more. So all of a sudden you see the lever you have by offering your customer a better efficiency. Yep. One thing is better base material. The other one is you put some insulating layer, some ceramic oxides on the surface, and this reduces the temperature of the metal itself, and you do it either by spraying or some electron beam vaporization technique, why can't we build that just half a centimeter? Again, don't forget, in operation, that ceramic layer might have 1100, 1200 degrees C, and then you shut the gas turbine off, and within 20 seconds, the temperature falls from 1200 to 400. And you can't do that often without that coating flaking off, and so you are limited in the thickness of that coating. How is that internal cooling done? You bring compressed air from the compressor and push it through some connections, some holes into the stationary and rotating blades. We have a hollow rotor, and we push some of the compressed air in here, and via some holes it goes, you see it here in the detail, into the hollow blade via some passages, does some internal cooling, and via those holes I have shown, it then puts itself around like a layer, a veil of cooler air around the circumference. Now you could think, all I have to do is take more of the compressed air to do more cooling, then I can raise that isotemperature. That graph tells you that only works to a certain extent. Here on the x-axis we have the temperature. And you can see at the beginning the isotemperature goes up and also the efficiency goes up. But if more and more of the compressed air is taken out from being a working fluid and becomes only a compression, only a cooling fluid, this air loses in part its ability to do work, and therefore if you exceed a certain level, all of a sudden the isotemperature goes down and the efficiency goes down. So depending on your cooling technology, you can only go up to a certain amount of cooling fluid before losing efficiency. And the amount of cooling air is not just 1 or 2%, it's in the range of 20, 22%, so it's a significant share. I mentioned the rotor. What does the rotor have to do? It is a long piece, maybe 10 meters long as this room. It should be very stable and not too heavy. Because it's too heavy, you can't fire it up quickly enough. Therefore, our concept is it is made up of individual thin discs, about that diameter, and held together by a central bolt, forcing it together. And on those discs, then you have the blades for the compressor and for the turbine. Again, I saw the graph in Professor Bohr's book. There is one more thing. You see one of those discs bladed for the compressor, but then you have to carry the torque, which the individual, for example, turbine disc gains from the hot gas through the whole turbine to the generator. So you have to have here some kind of a serration which allows you to carry the torque through the whole turbine. Again, each company has their own technique, but some kind of serration, nearly all of them have. GE sometimes said, we don't need any of that, but should I say, fortunately, they learned they need something to carry the torque. How are the different manufacturers designing their gas turbines? Nearly all of them have a length of 10, 12 meters, usually two bearings, one at the cold end compressor, one at the hot end of the turbine. The compressor is some 14 to 17 stages. The expansion side is 3 to 4 stages for the expansion. And I mentioned the combustion is either done into an open angular space, as Siemens did a long time ago, or in 1998 we bought our competitor Westinghouse. And when you buy a competitor, you learn a lot, because all of a sudden you see their drawing. So this is what they call a G501G, and it's quite similar. Also a 15 stages compressor built on discs. The combustion was done differently in those separate cans, and they also had some 4 stages of the exhaust turbine. The aerodynamic design was slightly different. They used a Rolls-Royce code. We had used a Pratt & Whitney code. We all asked for help from the jet manufacturers. Our strongest competitor for a long time, ABB, had a similar design till they came out with what they called the GT2426, which changes the basic thermodynamic process. They have a 2-stage combustion. And by doing this, you improve your process, and basically this concept could do 0.5%, 1% better than our design did. So we were quite shaky. Would they snap away all the contracts? They caught quite a few contracts, I have to admit. But that 2-stage combustion and the higher compressor ratio was also not without its problem. So, like we, also they had their share of a problem, which forced them to sell to Alstom, and Alstom got nearly broke on those problems. In the meantime, that engine is back on the market and doing well. There was another nightmare of ours. GE announced their newest H-type would break the threshold of 60% efficiency in combined cycle. They built one plant in the UK. I have not heard of any great success in the operation. I cannot comment. Should we say they built a very complex engine, and obviously building complex gas turbines has also its drawbacks. Also, we got infected with the bug. We have to have the most efficient gas turbine in the world, called the 8000H. But that design had one additional feature which could be of interest to you. As I said, we bought Westinghouse. So we had one American design for gas turbines, we had one European design of gas turbines. And if you want to develop further, you are in front of the question, do we develop 2, with making 2 times errors, and it costs a lot of money? Or do we try to get the engineers from Orlando, Florida, and the engineers from Mülheim together and build one gas turbine? And I can tell you, the pride of the engineers saying ours is the better solution is very strong, but eventually we overcame that by saying the Westinghouse guys should design the compressor or the combustion part. We design, or the guys in Mülheim design the expansion side. And so we gave everybody his share in the total development, and fortunately this 8000H, after quite a few years of development, we started in 2002, and the gas turbine went into operation 2008, 2009, and it turned out it proved that it can do what we promised. However, the development was very expensive. Maybe I'll make a comment on that in a minute. The gas turbine by itself can go up to efficiencies of 40%, maybe 42%, but a lot of the energy goes out with the hot exhaust gas. If the exhaust gas has some 550, 600 degrees centigrade, about 60% of the energy you fire in via the gas comes out as exhaust. That's not a very satisfactory solution. Therefore, people thought we can use those hot gases to make steam and combine the gas turbine with a steam turbine with no extra firing, and maybe that combined cycle, that's why it's named so, is doing better. And this is a well-known Sankey diagram. We bring in this example, about 685 megawatts in terms of heating value of the gas. The gas turbine has a net output of 268. And why that fat circle? Because about half the power which you generate in the exhaust side of the gas turbine is needed to drive the compressor. So the net, unfortunately, is only about half what comes out. And then in the combined cycle, you take the 60% of the hot gas into a boiler, a waste heat boiler, and provide steam. The steam cycle isn't that efficient, but at least you get in this case another 130 megawatts out without any extra firing, just some additional equipment. So in total, you get an efficiency of about 58%. And the power comes about 2/3 from the gas turbine and 1/3 for free in terms of fuel from the steam turbine. How does such a design look like? The reddish thing there is the gas turbine and the diffuser where the hot gas comes out. The grayish box is the largest piece of equipment in a combined cycle, the waste heat boiler. And we designed that combined cycle in a form that the steam turbine, this red part here, goes into the same generator. So the generator is driven from both sides. On one side from the gas turbine, at the other side from the steam turbine, and the sum of the two then gives the net output in those power lines going to the transformers. You can build that plant in such an open-air version as we do in many countries in the world. In others where you have a lot of snow and cold, you might want to house them into a turbine and a machine hall altogether. Those waste heat boilers are huge sheet metal boxes where you put the bundles of heating elements either horizontally or vertically, and since the exhaust is rather clean, you not only have tubes but finned tubes to increase the surface. Since one of the last efforts I undertook was this 8000H development, I'm happy to show you some of the slides. Upper part is the gas turbine. Down here, this is again the waste heat boiler, the gas turbine, the exhaust, and somewhere over here must be the steam turbine. And as we promised, the total output is close to 600 megawatts. We could do a little bit better than shown here. The first engine was measured by the local TEV, the licensing authority, to have an efficiency of 0.75%, and it runs rather well in many circumstances. This slide tells you where did that improvement of about 1.7% come from? What were the knobs we turned for that purpose? And we increased the pressure ratio, which gave about 0.2%. The main contribution, again, from raising the inlet temperature, we had an increase in component efficiency, better plates. We do preheat the fuel, and then also we have an advanced steam cycle, which results in those efficiency above 60%. In Germany, these days, with a lot of wind and solar power pushing their output into the grid, we get loads or energy input which cycles like this. In order to smoothen the total output, you need flexible units, and gas turbines and combined cycles are flexible. And in here, they had different system changes included, which allows that plant to come up about 3/4 of an hour faster. You would say, what is 3/4 of an hour? But if you start thinking that that engine might come only on twice a day for an hour, hour and a half, at noon when everybody tries to cook, and about between 5 and 7 when people again either cook or look TV, then if you can do 3/4 of an hour more of that period, then it pays off to the customer. Ooh, they have complex. Okay, so we are rather happy about that development, and me, I'm also happy about that, because when you spend about €500 million in the development, you would rather hope it turns out well. Okay, another important item is you can design that plant completely in a CAD and then execute it as it is on your computer. And maybe the final slide says, how are the costs distributed in such a combined cycle plant? The gas turbine, even though it's the key element, is only about 15 to 20% of the total cost. The steam cycle, you see, runs up to 40 to 50. The generator is relatively cheap. And then civil works, electrical makes up the rest. Again, what are the development areas? Again, the higher gas turbine inlet temperature, improved components, and make those plates last longer. If a set of plates is a couple of million, if they run 1,000 hours or 10,000 hours more, makes a difference. And on the steam cycle, it is just make the steam conditions somewhat better, meaning you raise the exhaust temperature, but then you run into a material problem for the waste heat boiler. So it's a difficult question how you go about it. So with this, I wanted to give you an idea what are the component challenges of a gas turbine. Thermodynamically, it's a rather simple cycle, even though looking through the graphs of Professor Prof, I see there is quite more than I understand. We think, engineers, the main problem was to get those components designed, fabricated, and installed, and in the end, give the customer a useful piece of equipment. Thank you. If you have questions, feel free to ask.
Так, большое спасибо. Какие вопросы? Профессор Riedle был бы рад на них ответить. Пожалуйста.
Professor, I'm an after graduate of Professor Burov. I would like to know more about your attitude towards increasing and about increasing the complexity of gas turbine cycles, about the intercooler or double burners.
We had quite a few sessions. For example, GE came out with the LM1000 with an intercooler. And we found out there is a number of full load hours between 2,000 and 3,000 where that piece of equipment would be better. When GE came out saying we are doing a steam cooling of the blades, again we said thermodynamically it gives a certain improvement. But in the end we said we only have engineering capacity, we only have a limited amount of money to develop new types, so we shied away from doing those complex pieces of equipment. You could say we were too thrifty, but if you get the number of $500 million for that 8000H, we looked, for example, at building something like the LM1000, and it was a minimum of 150 million, which would have been needed. And then we shied away, part of the money reason and part, don't try new things where you are not an expert.
So maybe another question. On Russian power, it's a great exhibition in Moscow held. I was talking with Siemens representatives, and they told that Siemens SGT 800 or 600, no, SGT S600, it is the gas turbine built and designed specially for combined cycle plants. It means that the parameters, the pressure ratio, the temperatures are designed in the way that in a combined cycle plant, the whole plant gives the maximum output and the maximum value. But all the logic of building the gas turbines in 200 megawatts, 300 megawatts, does this logic includes in combined cycle plants?
You are touching on a difficult item. If you decide we are developing a new gas turbine, then you would have to say one special one for open cycle and one for the combined cycle. But again, you're saying, do I have the engineering capacity to develop two? Do I have the money to test two? So we always said, let's design something which would work best for the combined cycle, but in a simple cycle also behaves properly. So the emphasis was more towards combined cycle. We never designed, at least for the large utility gas turbines, we never designed something to say, this goes only for open cycle or this would work only in combined cycle. Again, it's just also think about your factory. If you have 3 or 4 different types, that's fine. If you want to assemble 10 different types in one factory, the complexity also there gets more complicated.
Еще вопросы? Есть?
Поблагодарить надо еще раз. Еще раз поблагодарить.
Да, хорошо, давайте поблагодарим еще раз. Thank you very much.
Of that 8000H, my former people gave me some material, so if my English was not proper to your understanding, in those articles you could read a little bit more about that product.